Okay, welcome back. We're moving to section 2.8, algebraic surrogate equations. Okay, so any equation involving a radical, and this is what a radical looks like. An algebraic radical would be like that, or like this, and it might be equal to 3 or something like that. Any equation of that form is called an algebraic surrogate equation. Excuse me. And the thing inside the square root is called the radicand. Okay, so the radicand is inside and the whole thing is called a radical. So these can be also called radical equations. And the technique to solve them is to reduce them to quadratic form equations. So we're trying to reduce to ax squared plus bx plus c. That's the goal. But one of the conditions, or one of the particular characteristics of this process, is that square roots must be positive. And for that reason, rogue solutions, extraneous solutions must be rejected. So you should always check your solutions. The process is not foolproof, and the reason is very simple. We'll make a statement that the square root of minus 2 squared equals 4. Okay, now take the square root of both sides and you get 2 equals minus 2, which doesn't make any sense. Okay, so there's that, because having squared, when you square a number, you don't know whether it was negative or positive, and our process will churn out two answers. One of them will often be a rogue. And by thinking about using graphs or plotting the situation, we'll be able to determine whether there should be one or two solutions. Okay, so a Frere diagram will involve the definition. Okay, so we would have a radical containing variables. We nearly always work in one variable. Any radical that contains variables, any radical equation containing variables is an algebraic surrogate equation. Okay, here's a non-example. And that's a non-example because this is a perfect square, so this is the equivalent to x plus 3. Okay. Obviously the square root of x squared will be a non-example. The square root of 5x plus 2 equals 7 minus root x is an example. Okay. So the main idea is reduce to ax squared plus bx plus c equals 0 and check solutions. Could put a diagram in there too. A square root looks like this. It's half a parabola flipped on its side. Okay, let's go do this again. Okay, so solve x equals square root of x plus 6. So to remove the radical symbol will square both sides. Okay, now we'll identify this as degree 2. So we'll put all terms on one side. We'll try to solve by factoring first, which will be fine. We'll use the zero product rule. And we'll check. True. Sorry, that should have been a -6. So I'm going to squiggle because I'm not sure whether it's going to be equal or not. You saw I started off with a squiggle here. Then when I discovered it was equal, I came back along and said it was equal. So here I have -2 squared. It's being considered in its relationship with. Okay. So why am I squaring it? It should be just -2. So -2 is being related to the square root of 4, and that has to be rejected. Okay, so there's only one solution. X equals 3. Sorry about this, we done it earlier. Apologies about that. Okay, so this is where we have two radicands, and if you were trying to do these without ever having been shown what is the tried and tested way, here's several things you might consider. You might consider the surd conjugate of these by using a plus here, but that won't get you very far. You might try to square both sides, and again you'll end up in trouble. After lots of experimentation, or just by having seen someone else do it, you learn that you want to isolate one radicand, preferably the more complicated one. Okay, so this is a binomial radicand, and this is a linear radicand. So you'll try to isolate the radical with the more complicated radicand. Okay, and you get 2 plus the root of 2x. Now watch out with square roots, the length really counts. Okay, the origin of this line and the name of this grouping line in maths is a Vinchigum, I think it is. And it's the same line you see in a fraction bar, in the square root symbol. You can even use it to group instead of a bracket. You can write a plus b like that. Okay, so just be careful because there's often confusion in terms of where does the line end. Okay, that's why I tail it down like that. It's a very good idea to do that. Okay, so basically you need to learn this. You square both sides. So now we're squaring a binomial. So we'll square the first. I'll just write it in that form. I'll multiply the first by the second to get a cross product, but we'll want two of them. Okay, so that will be 2 times 2 root 2x, just to show you where it came from, and I'll square the last, which is plus 2x. Okay, now tidying up, I'll bring 4 back and cross it out. I'll bring 2x back, and I leave the 4 root 2x here. Okay, so we're disappointed that the radicand isn't gone, but if we double down with the squaring now, by squaring again, we should be okay. So here we go again, we're squaring the first, we're taking the cross product of 6x and doubling. Don't forget to double. Get your cross product, simplify to 6x, double to 12x. That should have been a square. And square the last. Square the 4. And square the radical, which just leaves us with the radicand. Okay. Take back the 32 by subtracting from both sides. Recognize there's a lot of multiplicity, there's 3 3s and 2 2s, so let's consider the multiplicity of this. Does it contain 3? No. Is it a multiple of 2? Yes. So don't split the 9. Do split the 2. I think I lost a sign there of minus as he came back. And go minus minus. Okay, we have factorized, but remember we're kind of going straight. We want to get the roots. So you can go to 2 9s or 2, because the roots are our target. So you don't have to be meticulously writing out that this is 9x take 2 by x take 2. You don't then have to be using the zero product rule painstakingly on each factor, because it's very clear that that gives 2 and this gives 2 over 9. So we have 2 candidate solutions, but they must be checked before we sign off on them. Okay, so we go back to our original equation, square root of 5x plus 6. Root 2x equals 2. And we can drop 2 in, giving 4 take 2 equals 2. And for the 2 9ths, I'd use a calculator. Yes, you can use fractions, but I'll quickly show you how to do it in a calculator. 2 fraction bar 9ths stored to x clear. We'll fill in the formula on the left. So this will spare us doing a load of fractions. You can hold your left thumb over your alpha button because you'll be using it a lot. Escape from underneath the radical sign, or the square root sign, you can call it if you want to keep things simple. And hit equals. And it is 2, so both roots work. Okay, and here we use technology to spare us working with fractions. I did it earlier by hand as well, but it's just a drudgery you don't need to go through. Okay, so just to say x is equal to 2 or 9 over 2, box it up. so now question 1. So we're heading in out of a lot of problem solving. So I'm going to be speaking to you as much on the process of problem solving, the art of problem solving and the craft of problem solving, as much as on the maths itself. Okay, I haven't worked these before, and that's very important. So I'm not looking at the solutions and just repeating them. I'm doing this as unseen problems, just as you will. So you should spend as much time understanding the problem as you will solving it. Okay, so don't rush the early bit. Enjoy it, take your time with it. Okay, but don't try to gobble it, to take it all in at one time. So once you get, so work piecewise. And the main, I suppose, instruction or advice I'd give you is to alternate between analysis and procedure. And keep going back to the drawing board and regrouping and rethinking about where you are. What the problem is, the thing that's going to work itself out for you. You can't do it all from the get-go when you don't know what you're doing, because you've never seen this problem before. So model, if there isn't a drawing, make a drawing. Now they're asking us to find an expression for the length of the diagonal. Okay, so maybe just draw that in a conventional way like this. So this is Pythagoras. The diagonal is equal to the square root of the sum of 2 squared. So staying inside the square root, we're going to apply our perfect square, which we realize we're going to have to do an awful lot of times in honors leaving cert maths. Very careful on that last plus. Okay, go for cancellations and then double up on the x squareds and the 2 4s. Okay, now that's in kilometers, so the distance equals this number of kilometers. Okay. So next up, we have a similar situation. There's an awful lot of writing there, so I'm sure it's a little bit more complicated. So we'll spend as long finding out what they're asking us as doing the actual solution. Okay, so the first of all tell us find the length of the diagonal. Okay, and the name is AC because it's going length AC. So let's write this in equation form. Length AC equals, the form of distance is always the square root of a square plus a square. So get all that done. You have 2 minus root 3, 2 plus root 3. Okay, we just work our way down the page, bringing it forward bit by bit as we analyze it. 2 2s is 4. That's 4 root 3 by the time you've doubled it. And careful here with the plus 3, because root 3 times root 3 equals 3. Okay, plus another 4, a plus 4 root 3, and a plus 3. Okay, so there is a cancellation. And then there is 14. And it's in kilometers. Okay, so we've got to here. One runner completes a full circuit all the way around, traveling at 1.5 meters per second squared. Okay, so let's go with the semi-perimeter first, which is 2 plus root 3 added to its surd. And the property of conjugates is that they add to become just an integer or rational. Okay, and that's the half perimeter. Okay, which implies perimeter equals 8. Okay, the diagonal equals root 14. So what is the question? A second runner runs from A to C and then back to A across the field at a rate of 1.4. So this is the perimeter, and the second runner runs to AC, which is equal to 2 root of 14. Okay, so the second runner time, let's say for the diagonals, for the two diagonals, equals distance over speed and the first runner is say running in the rectangle. They run 8 kilometers at a speed of 1.5. Okay, now something tells me I'm going to be subtracting then time difference. Okay, so I'm going to want to actually use letters that will fit in my calculator nicely. So I'll just call this X and I'll call this Y. Okay, so go to the calculator. Clear it. I'll pop open a side window for you there. Oh, I know. I have to take that off full screen. Don't know why, but I do. Okay, so here we go. So I have 2 root 14 over 1.4. Okay, and that's that. Which I'm going to store to X. I just didn't use A because it's been used for a point. And the second one I'm going to be calculating there. And I'm not too worried about which is going to take longer, because when I subtract them, I'll get either a negative or a positive value, and it doesn't really matter. Okay, so I have a fraction bar 8 over a speed of 1.5. Now, I have forgotten that these were kilometers. So in seconds, I need to put that as 8,000. Okay, I'm storing that to Y. And now remember, my X is 1,000 times too small. So I'll recall it. And I'll multiply it by 1,000. And I will store it back on top of itself. Stored to X. Okay. Now I'll calculate alpha X minus alpha Y. And get 11.89. And as I recall, they're looking for the time difference to the nearest second, so it's 12 seconds. And just to show them we've had that number 11.89. So this is why I went to write it. 11.8915. 11.8915. Just put a little bit into your short-term memory to write down and just say this is not rounded, it's just going on like this. And then say that that is, according to their instructions to give it, that is approximately equal to 12 seconds. And you can explain that that is to the nearest integer. Or anything, I just made that up, I haven't seen that before, but we often say 2 decimal places like this when it's relevant. You could say 0 decimal places. On to question 3. Again, I'm going to say spend as long reading the question and planning your strategy of approach as you will doing it. So he starts at G and walks along here. Counting the boxes, that's 4. Turns right and walks up to here. Counting the boxes, that's 2. But here's a fabulous trick, and I'm going to give you a special workshop on Pythagoras' theorem. Pythagoras' theorem is so simple if you write everything as a square root. So 4 is square root of 16, and you don't simplify. Just put everything you can in underneath the square root. Okay, 2 is square root of 4. And because, and then we're told that this length here is 2, which is the square root of 4. So now I'm going to calculate this. And remember, x squared is equal to the square root of a square plus a square. But when I put the square root of 4 in here, you see why I've done it. You see, well, the square root and the squares cancel. And that's the beauty of it. Okay? And because we're talking about x, well, actually, I'll put x, and I'll do all of this for you. But you're going to see how amazingly simple it is. X is equal to root 20. That's this x here. Okay? So now I've root 20 and root 4 at right angles to each other. So length, I can call it y for a second. I could call it kg. I could call it y is equal to the square root of 20 plus 4, which is 24. Okay, now we've closed the circle, the polygon. 1, 2, 3, 4. It's a quadrilateral, it's an irregular quadrilateral. And this is root 24. So now we can go back and write anything that can be written rationally as rational. So you got 4 plus 2 plus 2 plus root 24. And we can go further than that. We can take out the common 4 as 2 root 6. So that's the distance around, and we might look then to see other units and stuff we need to answer. Find insert form the exact distance travelled by Martin. There it is. Now just for fun, I'm going to show you another way, which is a little bit harder, but some might navigate around here slightly different. Or at least just think of the problem slightly differently. So you've gone with this being 16, of course, and this being square root of 4. Okay, but you were told this here is 2, so that's the square root of 4. And this is 1. Okay, now this is a subtraction, which makes this the square root of 3. And this is still 2. Now this is a messier way to do it, but it could have happened. Okay, now I have 3 here, which is the root of 9. And I have 2 plus root 3 here. And they will also give me the same value here, I would hope. So I'm going to go to the square root of 9, and I'm going to have to square 2 plus root 3, which is 4 plus 3 plus 2 root 3. Oh dear God, what's happening? 9 and 7 is 16. Okay, look, we already have the answer. Let's leave it at that. I think I was close enough getting it that way as well, but this was 1 away from 4 is root 3. This is root 3. This is 2 plus root 3. This is 3 and 1, 2, 3. Yeah, I mean, it's only purely for fun or trying to do it both ways. I'll leave it to you as an exercise. Okay. These are third conjugates. So when we add them, the reciprocal roots will go away. And when we subtract them, the minus on this minus will become plus, and you'll get 2 over root a, with the square root of a's cancelling each other. Okay? So now we know what their sum is and we know what their difference is. Now they're asking us to calculate the difference of 2 squares, which we know from the difference of 2 squares identity can be done in an alternative way with the exact same result every time, is this. So we can go the square root of 2 root a times 2 over root a, with the root a's cancelling, which is the root of 4, which is 2. That was easy. Okay, we're on to a straightforward square both sides situation here. Okay, and because there was no x's anywhere, there's no x squared, and this basically looks like one simple solution that we're finding. So 2x equals 8, x equals 4. Verify your answer with 2 4s plus 1 equals 3. Click or T for true. Okay, 5 I think is a huge number of parts, doesn't it? But these are very easy, we just run through them very quickly. Well, maybe not so easy. This time we have a quadratic, so we'll bring everything to the right. We will look for 2 numbers that are 3 apart, multiplying to 10. We will find the dominant cross product and make it negative. So we get 5 or minus 2. Now most likely this is rogue, but not necessarily. Yeah, you see why it's rogue. I'm going to put it in here. And you get negative 6 plus 10 is root 4. That's okay. It's the equals negative 2 bit that's not okay. So this is saying 2 equals negative 2, which can come about from the process of squaring and square rooting, or the other way around. If you started off with this and squared and square rooted, you'd get back to a true statement. But you would have started with a fake statement. So the other one to check if you want is 5. 3 5s is 15 and 10 is 25. So you get square root of 25 equals 5. And that's a valid solution. So you just keep the one solution. Okay, we're going to square both sides. And I'll just tell you what's going on here. You have this emanating from negative 8. Like a parabola going that way. You have this emanating from 1, like a parabola but steeper. You're getting one solution, maybe from a half, but you're getting one solution because these have different concavities, and so they can only meet once. Okay. And it happens at 9, out 9. And that's root 17 equals root 17. Okay, quick little analysis here graphically. You could do your trial and error as well. Start at 1. You're going to write out your numbers. 1, 2, 3, 4, 5. Okay. 2. 2 works, doesn't it? Root of 1 equals 1. So 2 is the solution. Now let's see, should we just stop at that? Because x with an intercept of minus 1 looks like this. And 3x take 5 starts back here and goes like this. Now, by the way, it's a monotonic increasing, meaning it always increases forever. It goes to infinity, so its range is from 0 to infinity. Okay, infinity isn't actually a number, so you put a curve on that and it can come all the way down to 0. So that's the range of square root. And we don't expect a second answer, so there's no point looking for one. Okay, and just for fun, we'll find that answer using algebra as well. But as I say, in an exam you wouldn't absolutely need to. You wouldn't need to at all. Two numbers multiplying to 6, adding to 5, 3 and 2. What is going on with the 3? Maybe there, so if there is a second solution, I've been telling you absolute rubbish about my diagrams and so on. And that's the beauty of using several tactics. Sometimes, you know, you make a conceptual error in one that's covered, that's discovered by the other. So we'll try 3 now. You get root of 9 take 5 is equal to 3. Oh no, is equal to 2. Okay, so 3 works as well, so we have 2 answers. I just want to go back and figure out how come that is. So 2 or 3 are the answers. Because this is amazing. This is a huge conceptual change for me. Because I gave you a drawing, it looked like that. Let me see. 3x take 5. So let's just solve 3x take 5 equals 0. At 5/3, which is 1 2/3, this graph starts. Now, by the way, this is at 1. So the graph starts here. It goes up and over, and it cuts twice. Okay, it doesn't maybe go up that steeply, but it goes up, and yeah, it does. It starts going straight up actually, just for an instant. You know, and that explains that. So you're starting your curve sketching proficiencies, and they're very important. So you'd be leaving out a whole facet of maths if you weren't doing these curve sketching. And you can see I learned something from question 5 there, question 5 part 4. I assumed there'd be one answer and I was wrong. Okay. I'm going to do it by inspection. 1, no. 2, yes. 10, no. 3, no. 4, 5, 6, 7, 8. Might be the only answer. I think once you found that low value, you'd say x equals 2 is one solution by inspection, and then you go on. Let's go x squared equals 4. Yeah, there's only one solution. Because that gives x is equal to plus or minus 2. And I think you have to reject. The minus 2 here would be minus 1 here. And it would be plus 1 here, you have 1. So did you notice when they're wrong, you often, when a solution is rejected, it often looks like a negative equals a positive. So that's interesting. So the one solution we wrote is the correct solution. Okay, the more complicated third is already isolated, so let's go ahead and square. Minus root x squared is plus x. So let's cross out the x's, which for a split second is a bit worrying, until we realize, well, there's still an x somewhere that we can leverage or pivot around to get a solution. Now there's a minus term here and a plus term here, so I favor bringing the negative this way. Did I have a 5 still here? I did. Okay, so root x equals 2, x equals 4. And we'll go back and sub that now. 4 root 9 equals 5 take 2, confirmed. One answer. This is a decreasing function, so I just want to show you a graph of this. This guy starts at -5 and goes like that. This guy, when x is null, for instance, starts at 5, which is way up here, and goes like that. And there's only one answer. He's allowed to go on down like that because, or he might. Let me see one. Might be one like that actually. Yeah, it's one like that. Put any of these into Desmos and you'd see what they look like. Oh, I should have squared there. Yeah, so now multiplicity, or looking at divisibility, this is not divisible by 3. So 9x stays intact with x here. This is divisible by 2, so the 2 has to split. Both negative. Get 2 or 2/9. Okay, I'm going to leave it to you to check then. Keep the more complicated radicand on its own. Square. Plus x. X's cancel. 14 root x equals 42. Root x equals 3. X equals 9. All we have to do is check it. Root of 16 is 7 take 3. Confirmed. Another thing you're getting used to, or you're trying to hone your skills on, is when you trying to stop putting brackets in if you really don't need them. But if they do help your thinking, if you're ever in doubt, you can put them in. But in terms of speed, they can slow you down. So if you don't need them, you should be putting them in. You know, you wouldn't want to be putting a bracket on that, just don't need to. Okay, we're going on here, and I might have made a mistake even. I've squared that, multiply that by that, but that's twice. Okay, that was a mistake. You'd be surprised if I made that mistake in school today too. So on we go from there, and this here simplifies to 2, comes back to another minus 2. By the way, here's another thing I'll say to you. Simplify both sides, otherwise you can end up just having too many variables and numbers and everything to juggle, and you'd lose track of what's what. You've too many balls in the air, so to speak. So you want to simplify left and right as to give you a kind of a goal to break it down. So here I see 4 take 2 is 2. And I have an x, and I have a radical turn. Okay, so now the x and the 2 need to go over to the left. And now we're squaring. Negative, and with 2 4s is 8, so it's negative 16x, and it's plus 16, and it's another 16, and it's just, and this time I will use a bracket. Okay, divide across by 4. Okay, and we do that distribution, we should have done it a while ago, equals 4x take 8. Now we'll bring terms back. Now we look for two numbers that multiply to 12 and add to 8. Okay, so x candidates are 2 or 6, but they both must be checked. 2 or 6. Putting 2 in, we're getting 2 on the left. Putting 2 in, we're getting 0 plus 2, which is perfectly good. Putting 6 in, we're getting root 16, we're getting 4. And we're getting 4. It's good, both are good. You might want to be saying that there. Was it just what I got there on both of them? 2 equals 2, 4 equals 4. X equals 2 gives 2 equals 2, verified. X equals 6 gives 4 equals 4, which is true, and it's verified. Doesn't matter, whatever you write it there, that's good enough. Page down. What have we here now? Well, first of all, we know how to turn compound fractions into single fractions, and that's another extra lesson you want to have if you can't do it from junior cert. Hence find this. Okay, so to turn a compound fraction, a over b minus c over d into a single fraction, by way of explanation, I'm going to put a d over d here, but in reality we don't do this. Okay, this is to explain why my method I'm about to show you, if you haven't seen it before, is done and works. Change the color of the pen and shut the whole thing down. Oh no, where were we? Okay, so maybe it'll let me change the pen now. Okay, so d over d gives us a common denominator both sides, and b over b gives us a common denominator. Okay, so what you have now is dA minus cb over db. Go back to the red stuff now, and I'll use a black pen. Say, but your dA comes from that. And minus CB comes from that, where you pick up the minus as you pick up the minus C as a factor. It's like saying this is plus with a minus in here on the C. Okay, and then multiplying D by B gives you this, and it doesn't matter if it's not the lowest common denominator. As long as it's a common denominator and you do this, anything extra will come out in the wash anyway when you simplify any fraction. Okay, and more than likely, if there's letters involved, it doesn't reduce anyway. So just remember, you multiply, plus multiply, or minus multiply, and divide by that. That's all you do. Okay, so we're going 1 by root 4x plus 8. So after our first multiplication, we get 4x plus 8, the square root of 4x plus 8. In the second multiplication, we get minus the square root of x plus 2. 4 is going to come out of here, by the way. And then you multiply the two together underneath. And while 4 is coming out of here, I'm just going to call this 2 times x plus 2. Because that's what we're multiplying together. So down at the bottom, we're multiplying 2 by the square root of x plus 2 by the square root of x plus 2, which is x plus 2. So I'll go 2x plus 4 down there. They didn't do that right. 2 of them take away one of them is one of them. Four is common. I can take it out. Easier still. Okay, now 1 over x. 1 over x plus 2 is now common. So I have 1 minus which is equal to 1 over the square root of x plus 2. So according to their expression, a and b are 1. Okay. Another thing, make this equal to 2. Okay. So 2 root x plus 2 equals 1. Or root x plus 2 equals a half, because we want the radicand in its own. Square both sides. Write the 8 over 4 in quarters just for convenience. And you get x equals minus 7 over 4. I'm going to make sure that that doesn't throw up something nasty. Well, it doesn't, because this is minus 7 over 4 and this becomes a quarter in here, which is 2. That's fine. Looks pretty standard, yeah? Factorizing is such a core skill as we see. 5 and 1. Domination. Negative. Positive. 5 minus 1 and check. Minus 1 will give minus 1 equals 1, which isn't allowed. And 5 will give 5 equals 5, which is allowed. Okay, so you can just scratch that out and say x equals 5. Don't spend ages explaining. Once you've crossed out the erroneous one, they love that. They know somebody knows what they're up to. You get full marks. So we're going to get an expression for this with a, isn't it? Cool. Let's go. Let's just hop in. X squared. Now when you're squaring, up to now we've been squaring a plus b, a binomial. I'm thinking about this today. How do we square a trinomial? Well, you group the first two and you go ahead and square. So, you know, we want to leave the two messy ones together. Let's see how we go. We're going to square this to get, because that won't be too bad actually. It'll be it'll be double the cross product, which is 2, because the root a is cancelled. And it'll be the square of the last. Now that's just the first squared. Now we have 1 times that, which is double that. Now we have the last bit squared, which is 1. Now that's just x squared, done. We have to subtract 2 of them. So just need a little bit of patience here for tidying up. I'm looking for like terms, which there are hardly any of anyway. So let's just wait on for the cleanup until we have everything in one place. So we are now going to take away 2, and remember, don't bite off more than you can chew. So I'll put a root a plus a 1 over root a in there. And I'm going to continue on from where this 1 is, because the last thing I want is to have to write all that out again. So minus 2 root a minus 2 over root a. And I expect a lot of cancellations, so let's see where our cancellations are. There and there anyway. So now we're just looking back this way. We have 1 and 2 is 3. And we have a plus 1 over a. And that's that answer. We have a quick look at the solutions and see, do we like it? What number? 9. Yep. Did I have a single one? I hope I did. A plus 1 over a plus 1. I'm sure I had a plus 1. Let's look back and see. 3. I must have missed some cancellation. There should have been a minus or something. X squared minus 2x. Oh, minus 2. You know what? I left out, did I? Yeah, I left out minus 2 of them. That should have had a plus 1 there, which would have put a minus 2 here. Should have turned that into 1. Sorry about that. Slips will happen. I would have had no way of knowing an example of that. A and B are positive integers. Find the values of A and B. Now they're positive integers, so you could just go fishing. And they're not equal to each other, because if they were, there'd be no square roots here. But I'm not going to fish. I'm going to work it out. So I'd like to arrange things. If it's not a binomial expansion, if the two binomials are different, I like to write them vertically. So I have AB, I have minus 3, and the two partial products are not like each other. So I have plus B root 3 and minus A root 3. Now here's where things get interesting. It's equal to 7 plus 3 root 3. So this wasn't taught to us anywhere in this section. And it's this. The whole numbers must give an equation. So AB minus 3 equals 7. And the thirds, the square root 3's must be correct. So B take A equals 3. Okay? Now this is non-linear and this is linear. So we're going to put sub B as 3 plus A. So now we have A on 3 plus A equals 10. So I'll pop him across. Or no, I won't, because I'll have to bring it back in a second. Okay, A squared plus 3A minus 10 equals 0. So that's what we know where we're going here. A and A, 5 and 2. That's positive. That's negative. So A equals 2 or minus 5. And what usually happens here is you're swapping over and back between them. You see B is 3 larger than A. Yeah, so B is 5. And we'd have to check both of them, but they did say they were both positive, so this has to be rejected. We can write that as AB equals 2, 5. I think I know what's going to happen here because I've just seen it so often. So if I'm right, there's a 3-dimensional Pythagoras. We'll just see. The length of an open rectangular box is 2 meters longer than its height. Call it x. And 2 meters shorter. The width is 2 meters shorter. So x take 2 and x plus 2. Okay, luckily they used the same letter I did. And it's entirely what they come down to here, because if you're trained well, you'll be already putting in a variable up here. That's just nasty. Okay, let x be the height in meters and find an expression for the diagonal from I to C. So what this is, it's leading us. They could have told us we just get the 3-dimensional diagonal. But with IC, I just get to keep track here and see that there's an x plus 2 and an x minus 2. Okay, so square root for distances, x minus 2 squared plus x plus 2 squared. That's just Pythagoras. Used for distance, you know, the distance formula has a square root in it. Okay, and we might as well just use the notation IC, distance IC. Now I'm going to have to do a bit of work here by completing these squares. X squared minus 4x plus 4. And no reason to use a bracket. X squared plus 4x plus 4. So 2x squared plus 8. And now they're going to go on and ask us to use this, which is x, and then to get this distance. There is a way of getting it directly, which I'm going to show you too. The diagonal I to D. Yeah. So to do this, we want this, which is x. So basically, we're going to be going in with the square of this plus x squared. I'll show you an easier way in a second. So this escapes the radicand. And you get 3x squared plus 8. That's probably it. But there's an easier way, and it's this. So for a cubed root, for a square, for the distance across a 3-dimensional box, we just use all 3 of the things squared. Okay, so was it x minus 2, x plus 2, and x? Was it x? Yeah. So that would have given us an x squared and a 4, and the other stuff will cancel with this bit, so we'll leave it out. Another x squared and a 4 and an x squared. And look how much easier that would have been. So this is all I would do if they didn't take me on a silly merry-go-round or they're trying to teach us the maths that we already know because we've been studying for Leaving Cert. So you get 3x squared plus 8. This is part of the problem with project maths. You kind of have to, I think that's the end of it there. You kind of have to appease the examiner by doing all the jumping through the hoops they ask you to do, because they don't think you know maths, before you get to the meaty bit, which was always the target for questions traditionally if you look back through old question papers. So you can end up doing a lot of mundane, simple things at the beginning before you actually do the hard question, where it's far more rewarding when you just got straight down and did the difficult maths. That's just something we have to live with the new style of papers. It's not too bad though with Leaving Cert, it's much worse at Junior Cert. So I would just say that the Leaving Cert papers are still quite rewarding and it's quite enjoyable to do. So keep your motivation up. And this is really tough going for you. So it's going to take some time, take some practice. But you're overlearning as well with these exercises, because the exam papers, the amount of interconnection between the sections and the exam papers are a bit easier. They're not as dragged out, so you're going to be fine. See you in the next one.